The maintenance of genome integrity is fundamental to healthy aging and cancer prevention. Every day, cells experience a barrage of DNA damage from internal sources like oxidative stress and replication errors, as well as external insults such as UV radiation or environmental toxins. While cells possess robust DNA damage response (DDR) systems to detect and repair these lesions, these mechanisms decline with age. When repair fails or becomes inefficient, cells face a dangerous choice: continue dividing with mutations, enter senescence, or trigger apoptosis. Here, autophagy plays a pivotal, though often underappreciated, role in managing the fallout from genomic instability by removing the most dangerous elements before they become a systemic threat. Autophagy functions as the cell's cleanup crew, and its role extends beyond degrading worn-out proteins and organelles. In the context of DNA damage, autophagy helps eliminate cytoplasmic DNA fragments, micronuclei, and even entire cells that carry high mutation burdens or chromosomal instability. These damaged components, if left unchecked, can activate inflammatory signaling pathways such as cGAS-STING, which fuel chronic inflammation, senescence, and cancer progression. By clearing this debris, autophagy prevents the persistent immune activation that underlies many age-related diseases and contributes to tumor-promoting environments. In aging cells, the relationship between DDR and autophagy becomes especially important and precarious. As DNA repair becomes less efficient with age, cells accumulate mutations at a faster rate. Autophagy is one of the few remaining systems capable of mitigating the damage. When autophagy is functional, cells with unrepairable or severely compromised genomes can be targeted for degradation or removed through processes like mitotic catastrophe or autophagic cell death. This helps prevent the survival of potentially cancerous cells. In contrast, when autophagy is impaired, a common occurrence in aged tissues, these defective cells persist. They may enter senescence, releasing pro-inflammatory factors that damage neighboring cells, or worse, bypass cell cycle checkpoints entirely and initiate tumor formation. The implication is clear: autophagy serves as a final line of defense when DNA repair fails. Its decline with age removes a vital barrier against both cancer and degenerative disease. This interconnection issues a warning: supporting DNA repair without maintaining autophagy may allow mutated cells to survive longer than they should. Similarly, promoting autophagy in the presence of high genomic instability without proper safeguards could enable mutated cells to recycle themselves into a more resilient state. Autophagy, if not carefully regulated, can protect healthy cells or embolden dangerous ones depending on the context. Nevertheless, there is a powerful therapeutic potential in this pathway. Interventions that restore autophagy, such as intermittent fasting, NAD+ precursors, or compounds like spermidine and rapamycin, have been shown to enhance DNA damage responses and improve cellular resilience. These treatments do not necessarily prevent DNA damage from occurring, but they improve the cell's ability to respond, either by enhancing repair, initiating cell cycle arrest, or removing dangerously unstable cells before transformation occurs. Animal studies show that stimulating autophagy slows the accumulation of senescent cells, reduces chronic inflammation, and lowers cancer incidence, all signs of a healthier genomic landscape. Still, the practical application of this approach in humans must be done cautiously. Older adults, in whom both DNA repair and autophagy are already impaired, may have a diminished capacity to benefit from interventions that rely on a strong underlying autophagic response. Moreover, in individuals with existing precancerous lesions or undiagnosed tumors, stimulating autophagy could have mixed effects, eliminating some unstable cells while allowing others to adapt and survive. In essence, autophagy acts as both a repair assistant and a cellular executioner in response to DNA damage. Its ability to eliminate genomically unstable material is central to the body's defense against aging and cancer. When it declines, as it does with age, the result is a cellular environment where errors accumulate, inflammation rises, and the risk of malignant transformation grows. Supporting autophagy, particularly in midlife before widespread dysfunction sets in, may be one of the most effective strategies to maintain genomic stability and extend healthy lifespan. Autophagy is not just about recycling, it is about quality control at the most fundamental biological level. By clearing the wreckage left by imperfect DNA repair, it prevents dangerous mutations from gaining a foothold and buys the organism time to adapt, recover, and continue functioning. As a mediator between damage and repair, autophagy stands as one of the last lines of defense against the chaos of aging. And with the right timing and tools, it may become one of our most powerful allies in the fight against cancer and degenerative decline.